Imagine you have collected data from 10,000 students. You have their age, CGPA, branch and placement status. But when you open the data sheet, you discover that thousands of values are missing. Now the question is, can we simply delete them? Can we replace everything with the average? And what if the fact that a value is missing actually tells us something? That's exactly what we are going to explore today. Hello friends, I am Boyobde and you are watching Unplanned Pulse. Let's start. Before we train any machine learning model, there is one very important state that we cannot ignore, and that is data pre-processing. In the real world, the data we collect is rarely perfect. Some values may be incorrect, some may be duplicated, and very often some values may be simply missing. For example, imagine that we have a datasheet containing information about students. We may have their age, CGPA, branch and placement status. But what happens if the age of one student is missing or the CGPA of another student is not recorded? That is what we call missing data. And today we are going to learn how to identify missing values, understand why they occur, and most importantly, how to handle them correctly in machine learning. By the end of this video, you will understand everything from simple techniques like mean, median, imputation to more advanced approaches like KNN, regression and mice. So let's start from the very beginning. Now let's know what are missing values. Let's first understand what a missing value actually means. Consider this simple student datasheet. We have information about 4 students, including their age, CGPA, branch and placement status. But notice something. For student B, the age is missing. For student C, the CGPA is missing. And for student D, the branch is missing. These are called missing values because the actual information is unavailable. Depending on the data sheet, missing values can be represented in different ways. You might see NaN, null, none, a question mark, an empty cell, or even a word like unknown. Although these representations look different, they all indicate one important thing. We don't have the actual value for that particular observation. And before giving this data to a machine learning model, we need to decide what to do with these missing values. Next, we will know about why are missing values a problem. Now, you may ask, why do we even need to handle missing values? Why can't we simply give the datasheet to our machine learning model? The problem is that many machine learning algorithms accept complete input data. For example, imagine that we want to calculate the average of students' age. If one of the value is missing, we cannot simply perform the calculation as if that value exists. Similarly, many machine learning algorithms cannot directly process missing values. And even when an algorithm can technically handle missing values, ignoring the problem may still affect the quality of our model. Missing data can lead to loss of useful information, biased result, incorrect statistical analysis, and poor predictions. So, missing values are not just an inconvenience, they are a data quality problem that we need to handle carefully. Let's know about types of missing data. This is one of the most important theoretical concepts in missing data. So listen very carefully. There are 3 types of missing data: MCAR, MNAR and MNAR. The first type is MCAR, which stands for missing completely at random. This is the simplest case. Here, the probability that a value is missing is completely unrelated to the data. For example, imagine that we have a survey database, and because of a random technical error, some salary values are accidentally deleted. The values are not missing because of person age, salary, gender or any other characteristics. They are simply missing randomly. This is called missing completely at random or MCAR. In mathematical terms, we can think of the probability of missingness as being independent of the data. MCAR is generally the easiest type of missing data to handle. The second type is MNAR or missing at random. Here the missingness of one variable depends on another variable that we can actually observe. For example, suppose we have a survey asking people about their income. We notice that younger people are more likely to leave the income field blank. Here the income is missing, but the missingness is related to age, and the age is something we can observe. So the missingness depends on a observed variable. This is called missing at random or MAR. This is more complicated than MCAR, but we can often handle it using information from the other observed features. Finally, we have MNAR or missing not at random. This is the most difficult case. Here the reason is that value is missing is related to the value itself or to some unobserved factor. For example, imagine that people with extremely high incomes are less likely to report their income. In this situation, the missingness of income is related to the actual income value, but the actual value is precisely what we don't know. So now we have a difficult situation. The missingness itself may contain information about the missing value. This is called missing not at random or MNAR. So to remember the three types, MCAR means completely random, MAR missingness depends on observed information, and MNAR means missingness depends on the missing value itself or an unobserved factor. Understanding these three types is important because the correct handling strategy depends on why the data is missing in the first place. Before we handle missing values, the first thing we need to do is detect them. We should ask three basic questions. First, which column contain missing values? Second, how many values are missing? And the third question should be, what percentage of the data is missing? For example, imagine that our datasheet contains four features: age, salary, CGPA and branch. Age has two missing values, salary has 20, CGPA has 1 and branch has none. But the number alone is not enough. We should also calculate the percentage. Here, salary has 40% missing data if we calculate. That is very different from age having only 5% missing data. This information will help us decide whether we should delete the data, replace the missing values or use a more advanced imputation technique. The first approach is deletion. The simplest method is row deletion. If a row contains missing values, we simply remove the entire row. For example, here we have 3 students, but the age of one student is missing. So we simply can remove that student's entire record. This method is very simple, but there is a major disadvantage: we lose data. And if a large percentage of our datasheet contains missing values, deleting rows can significantly reduce the size of our training data. Therefore, row deletion is generally appropriate only when the number of missing rows is very small and we have enough data available. The second deletion method is column deletion. Suppose we have a feature called salary, but 90% of its value are missing. In such a situation, trying to estimate almost the entire column may not make sense. If the feature is not essential to our problem, we may decide to remove the entire column, like this. However, we should not delete a feature just because it contains missing values. We need to consider how important that feature is, how much data is missing, and whether we can recover useful information through imputation or not. So deletion should always be a decision based on the datasheet, not a rule that we blindly follow. Now let's move to the second major approach, imputation. Imputation means replacing a missing value with an estimated or reasonable value. Instead of deleting the entire row, we try to preserve the data by estimating what the missing value could be. There are many imputation techniques. Some are simple, such as mean, median, mode imputation. Others are more advanced, such as KNN imputation, regression imputation and mice. Let's understand them one by one. The first imputation technique is mean imputation. Suppose we have the following ages: 20, 22, 24 missing, and then 26. We calculate the mean of the missing value with 23. Okay. Now we can replace the value 23, which comes out as mean, with the missing value. Mean imputation is simple and fast. It works reasonably well when we have numerical data that is approximately symmetric and does not contain significant outliers. But there is an important problem. The mean is highly sensitive to outliers. For example, if we have values like 20, 21, 22, 23 and 1000, that value of 1000 will significantly increase the mean. Therefore, mean imputation is not always the best choice. The next technique is median imputation. The median is middle value when the data is arranged in sorted order. Consider these values 20, 21, 22, 23 and 1000. The value 1000 is an extreme outlier, but the median is still 22. This is why median imputation is often preferred when the data is skewed or contains outliers. So, any missing or empty value in that data sheet will be replaced with the exact output value of 22. So remember this simple rule. Mean is often suitable for approximately symmetric numerical data, and median is often safer when the data is skewed or contains outliers. Now let's look at categorical data. Suppose the branch column contains CSE, ECE, CSE, CSE and one missing value. The most frequently occurring category is CSE. This is called the mode. So the CSE will be the mode. So we can replace the missing value with CSE, right? Mode imputation is commonly used for categorical features such as branch, gender, city or department. However, we should remember that this can change the distribution of our categories, especially when there are many missing values. Another approach is constant value imputation. Here, instead of estimating the missing value, we assign a fixed value. For categorical data, we might use a category such as an unknown or not available, like this. This can be useful when the fact that a value is missing is itself meaningful, but we should be careful about using arbitrary values. For example, replacing a missing age with 0 does not mean that the person's age is actually 0. It simply means that we don't know the age. So, in many cases, using a meaningful category such as unknown is better than using an arbitrary numerical value. Now, let's look at methods that are particularly useful for time series data. The first is forward fill. Here we replace a missing value with the previous available value. So if Tuesday temperature is 31 and Wednesday temperature is missing, we may use 31 like this. So the question mark of the place will be filled by 31 here. The second one is backward fill. In this case, here we will use the next available value. So if Thursday temperature is 33, we may use 33 for the missing Wednesday value. Another technique is interpolation. Instead of simply copying the previous or next value, interpolation estimates a value based on the surrounding observations. For example, if Tuesday is 31 and Thursday is 33, we may estimate Wednesday to be approximately 32. These methods are especially useful when the data has a natural, sequential or time-based relationship. However, we should be careful because these assumptions may not be valid for every datasheet. Now let's move to a very more intelligent technique called KNN imputation. KNN stands for K nearest neighbors. The basic idea is simple. Instead of replacing a missing value with the same value for everyone, we look for data points that are similar to the observation with the missing value. For example, suppose we have information about students including age, CGPA and salary like this. One student's salary is missing. Instead of simply using the average salary of the entire datasheet, KNN looks for students who are similar based on the available features. It then uses the information from the nearest neighbors to estimate the missing value. This can be more accurate than simple mean or median imputation when strong relations exist between the feature. However, KNN can be computationally expensive, especially for large datasheets. It is also sensitive to feature scaling because it relies on distance calculations. To find exact estimated value of student C, let's calculate it using k equals to 2, the two nearest neighbors, with a standard Euclidean distance formula and simple average. Our first step will be normalization. You can see the process here. After this, we will calculate the distances from student C like this using the Euclidean distance formula. And then we will select the two closest student to student C as k equals to 2. And now if we calculate the average of the salaries from these top two neighbors or students, we will get the estimated missing salary of C, like the final answer written here. So this is how we can calculate. Another advanced technique is regression imputation. Suppose our salary column contains missing values. We may have other available features such as age, experience and education. We can use these available features to build a regression model that predicts salary. Conceptually, we are learning a mathematical relationship like salary is a function of age, experience and education. Let's look at our example. So this is our example table. We have students A, B and D, and C's salary is missing. Instead of just taking the average of 30, 35 and 45k, we use the known data to calculate a line of best fit. By applying the simple linear regression formula, let's show you how the model predicts the value. You can see the formulas here. At first, it calculates the slope and intercept for the line of best fit. Our model learns the exact mathematical relationship. It finds the slope is 5 and the intercept is minus 70, giving us the equation salary equals to negative 70 plus 5 times age. Once the model learns this relationship, we can use it to estimate the missing salary value. We simply plug student C's age, which is 22, into our equation. Negative 70 plus 5 times 22 gives us exactly 40k. The advantage here is that we are using actual mathematical relationships between features rather than simply using one global value such as the mean. However, keep in mind the quality of imputation depends entirely on how well your regression model captures that underlying relationship. Now, let's discuss MICE. MICE stands for multiple imputation by chained equations. This is a more sophisticated statistical approach designed for complex datasets where multiple variables contain missing values. The basic idea is that we use the available variables to estimate missing values in other variables. Let's look at an example. So this is our example table. Imagine we have a datasheet where student B is missing their salary and student C is missing their age. First, MICE initializes the datasheet by filling the blanks with simple averages just as temporary placeholders. Then the chain begins. We erase student B's temporary salary and build a model to predict it using age and experience. Okay, so you can see we have made a temporary table by finding the age and salary. The next step will be by deleting them. Now, once we get better estimate for students B's salary, we lock it in. Next, we move to student C. We erase their temporary age and build a new regression model to predict age using salary and experience. We now use the updated data from student B to help make decision about the predicted salary or predicted age, right? So this will be the final table after calculating their age and salary. This process is repeated through a chain equation. We cycle through age, salary, experience and education, updating the missing values one by one, over and over, until the numbers stabilize and stop changing. MICE is incredibly powerful, useful for complex than simple mean or median imputation. Can take more time to compute and requires more careful statistical assumptions. Now, let's discuss a very interesting topic. Sometimes the fact that a value is missing can itself contain information. Suppose we have a income feature. Some people provide their income like this, okay, while others refuse to answer. If we simply replace the missing values with the median income, we may lose the information that these particular people actively refuse to provide their income. One powerful solution is to create an additional feature called a missing indicator. For example, we add a new column like this. A 0 means that the original value was present, and a 1 means that original value was missing at the column income missing. Okay, it is working as a indicator, missing indicator, you can say. This way the machine learning model gets two pieces of information: the estimated value and the fact that the original value was missing in the first place. This can sometimes drastically improve model performance, especially when the missingness itself is informative, like a customer hiding their income because it's very low, or a sensor falling because the machine is overheating. Let me give you one more example for clear concept of it. Suppose, imagine a loan application datasheet. Person A earns 1,50,000, happily writes it down, and person B earns 15,000 and leaves it blank out of embarrassment, right? If we just use median imputation, the system feels person B's income as 50,000, the average. The model now thinks person B is financially stable, but if we follow this rule, the income missing will be 1. The machine learning model learns a new rule: whenever income missing is 1, this person is actually a high risk borrower, regardless of the 50,000 imputed value, right? Now we come to one of the most important concepts in machine learning pre-processing, is data leakage. Suppose we have our data sheet split into training data and testing data. A very common mistake beginners make is to combine both data sheets and calculate the mean or median before performing imputation. This is wrong. Why? Because the test data was now influenced our pre-processing process. The model has indirectly received information from the test sheet. This is called data leakage, and it will give you a falsely high accuracy during the testing that will completely crash in the real world. The correct approach is to first split our data sheet into training and testing data, then we calculate the imputation value using only the training data, right? For example, we calculate a median using the training set. We use the median to fill missing values in the training set, and this is the crucial part. We use the exact same training median to fill missing values in the test set. The test set should never ever influence the calculation of our pre-processing parameters. This principle applies not only to missing value imputation but also the scaling normalization and other pre-processing techniques. So remember the golden rule of data pre-processing: fit your pre-processing on the training data, then use the learned transformation on both the training and the unseen test data. You can understand it like this: the training set is your practice exam and the test set is your final exam. If you calculate the mean using both, it's like looking at the final exam questions to help you study for the practice exam. You are leaking the future into the past. In the real world, when you deploy your model, you would not have the future data to calculate a mean with. So your pre-processing must strictly rely only on the training data. So how do we choose the correct method? There is no single magic method that is best for every datasheet. The decision depends on several key factors. Like first, how much data is missing. If only a teeny percentage is missing, simple imputation may be completely fine. But if a feature contains an extremely high percentage of missing values, we may consider removing the feature entirely, especially if it is not critical to our model. Second, what type of data do we have? Looking at the board, we break this down into 3 parts: numerical data, categorical data, and time series data. In numerical data, we can consider the mean, median, KNN, or regression based methods. For categorical data, substituting the mode or creating an explicit unknown category may be the most appropriate thing. For time series data, techniques like forward fill, backward fill, or interpolation are incredibly useful. Finally, we should ask whether there is strong relationship between features. If there is, advanced methods such as KNN or regression or mice will provide much better estimates than simple averages. So the key takeaway is not to memorize one universal method. Instead, you need to deeply understand your data, observe its relationships, and choose the pre-processing method that makes the most mathematical sense for the specific problem. Let's now put everything together into one complete machine learning workflow. We start with our raw data sheet. First, we inspect the data and identify missing values. Then we analyze how much data is missing, try to understand exactly why it is missing. Next, we split our datasheet into training and testing sets. This step is absolutely critical because we must avoid data leakage. We then choose an appropriate imputation technique. We learn the required imputation parameters like mean, median, or a regression equation. Using only the training data, then we apply that exact same transformation to both the training and testing data. After that, we continue with our pre-processing steps such as encoding categorical variables and scaling numerical features. Finally, we train our machine learning model on the clean training data and evaluate its true performance on the unseen test data. And that is how missing value handling fits perfectly into the larger machine learning pipeline. So let's quickly summarize what we learned today. Missing values are observations that are unavailable in our datasheet. Before handling them, we should always identify how many values are missing, which features are affected, and why the values are missing. We learned about 3 important types of missing data: MCAR, MAR, and MNAR. MCAR is where missingness is completely random. MAR is where missingness depends on observed variables, and MNAR is where missingness depends on the missing value itself or an unobserved factor. We also learned 2 major approaches for handling missing values. The first is deletion, where we remove rows or columns. The second is imputation, where we estimate and replace missing values. For simple imputation, we have mean, median, mode, and constant values. For time series data, we can use forward fill, backward fill, and interpolation. For more complex situation, we can use advanced techniques like KNN, regression-based imputation, or mice. We also learned an extremely important machine learning concept called data leakage. We should always learn our pre-processing parameters from the training data and then apply that exactly same transformation to the test data. And finally, remember this: there is no universally best method for handling missing values. The correct approach depends on the type of data, the amount of missingness, the reason behind the missingness, and the relationship between different features. So don't blindly replace every missing value with the mean. First, understand your data, then choose the method that makes the most sense, and that is absolute key to handling missing values effectively in the machine learning. Okay? Thank you for watching Unplanned Pulse, and I will see you in the next lesson. Thank you.